Okie dokie. We are jumping then back into chapter 1, and we will start chapter 2 today as well. Did we get to this slide on Friday? Okay, I didn't think so. Okay, so we had finished talking about the teeter-totter with blood or body temperature, and we said that was an example of a negative feedback mechanism. Okay, what happens in a negative feedback mechanism? Your goal is to bring something to somewhere. What are you doing? Yeah. Exactly. So it's a teeter-totter. You're bringing it back to level, back to balance. Okay, so that's negative feedback. Then the opposite of that is positive feedback. So what happens in positive feedback is you're enhancing whatever's going on. So instead of bringing the teeter-totter back to level, you're saying, oh, we've moved a little bit, let's go like this. Okay, and you're just throwing things all out of whack. So, as you might expect, this doesn't happen a lot of places in the body, okay? Because we really want to maintain homeostasis. But an example of this positive feedback mechanism is during blood clotting. Okay, so you've torn a vessel and you're bleeding. Okay, you need to form a clot. So you start forming a clot with platelets. Platelets will start sticking together and you'll form a beautiful little clot. But to start with, it's not very big. Okay, it's pretty small. So once those platelets stick to each other, they'll release clotting factors. So they'll release more factors that say, come on in, more platelets, and more platelets will be released, and they'll come form the clot with those other platelets. They'll join to them. When they join, they release more clotting factor, which causes even more platelets to be released to come join the clot. Okay? And this keeps going until we have a nice big clot to close off the blood vessel. Okay? Yeah. So Band-Aids help keep things more contained. They help keep microbes and other things like that out of the area. But they're not doing a whole lot to actually cause clotting. Okay, they're just keeping that environment safe until clotting happens. Yeah. Okay. So blood clotting is one of these examples of positive feedback. We are increasing the effect. What's another example that you can think of? Yeah. Childbirth. Right. So in labor, your body starts to these signals that say, hey, this baby needs to come out. And so you have a contraction. That contraction pushes the baby's head down towards the cervix. When it pushes down, it causes the release of more hormones that go back and say, we need more contractions. That contraction pushes the baby down even more, which stretches even more, which releases more hormones, which cause more contractions. Okay, so we keep that process going until there's no longer a head there pushing on the cervix to stretch it. Okay? So that means the baby has been born and we can stop it. Okay? Lactation, so milk production is another example of this. Once it starts coming out, it keeps flowing for a while. So there are a couple of examples of positive feedback mechanisms, but a lot of our physiological examples are those negative feedback mechanisms. Okay? All right, that is all that we're going to say about homeostasis right now. Now we're going to move on to more anatomy stuff, so anatomical position. So what is, can anybody demonstrate for me, the anatomical position for a human? Yeah. Very good, very good. Okay, so you're standing up, facing forward, and your feet are slightly apart, and your hands are palmed forward with your thumbs out. Okay, so that's anatomical position. And you should have looked at a lot of this stuff in your lab activity for last week. Okay, so some of this should be reviewed for you guys. Okay, so we've got anatomic position. Now that we're in anatomic position, we can tell how things are related to each other. Okay, so we have some directional terms. Now, the thing to remember about directional terms are they are comparative. So you're comparing two things to another. Okay, I'm going to put this chart up. I realize it's really, really small, but we're going to demonstrate here. Okay? So the first two terms are superior and inferior. So superior is the opposite of inferior. Okay? So superior is closer to your head. Inferior is closer to your toes. So what is superior to my nose? My forehead. Okay, what is inferior to my nose? Your mouth, your teeth, anything like that. Okay, so superior and inferior. Superior, you may also see it cranial, because your cranium is your head. And you may see inferior as caudal, C-A-U-D-A-L? Yes, D-A-L, which means tail. So your inferior is your tail region. Okay, the next two are anterior and posterior. Anterior and posterior. Anterior, you may also see as ventral, and posterior, you may also see as dorsal. Okay? The anterior is closer to the front when you're in anatomic position. Posterior is closer to the back, again, when you're in anatomic position. So that's going to come in handy with your hands, right? So if this is anterior, this is posterior. Even if you kind of hold them like this. Okay? This is always the anterior side. This is always the posterior side. Okay? Medial and lateral has to do with that middle plane of your body. So medial is something that's closer to the middle, and lateral is something that is farther away. Okay? So my shoulders, are they more medial or more lateral? More lateral. Okay, so it's closer to the outside of the body. Okay? Intermediate is between, is more medial and a more lateral, is between a more medial and a more lateral structure. Okay, so if you have like three things, there might be something that is medial, something that is lateral, and something between them would then be intermediate. Okay? All right, proximal and distal. These are the two that usually give people problems. Okay, the thing to remember with proximal and distal is that you use them when you're talking about limbs. So arms and legs, proximal and distal. So proximal is closer to the trunk, to the body. Distal is farther away. It's a farther distance away. Okay? So what is something that is proximal to my elbow? Shoulder is proximal, closer to the body. What's something that's distal to my elbow? My hand, my wrist, anything in this region. Okay? But proximal and distal refers specifically to your limbs. Okay? And then superficial and deep. Superficial is going to be something that's closer to the surface of your body, and deep is going to be something that's deep. I know, that's amazing, right? Okay, so your heart is deep, your skin is superficial. Okay? So, now that we know those terms, I want you to find some people that are close to you, distance-wise. Read this question and see if you can choose which one is the most of the terms. So which one is the most distal, the elbow or wrist? Which one's the most lateral? Okay, you don't have to write it down, you're just chatting. This is a little checkup, see if we know what's going on. Then we'll talk about it. Okay, you're getting a little bit quieter, so let's see how you did. Distal, which one's the most distal? The wrist, good. Which one's the most lateral? Hip bone. What's the umbilicus? Your belly button. Okay, which one's the most superior? Your nose. Which one's the most anterior? Toes. And which one's the most superficial? Perfect, good job. Okay, so we got our directions. Next are going to go through and point out all the different things. Okay, you've got the picture here to study. This is one of the diagrams that you need to know for your test. Okay, so under there's one objective that has a list of, you need to know the regional terms, you need to know anatomic position, that type of thing. This is one of those diagrams. Okay, so you'll see this diagram on the test with arrows to certain things that say, hey, what's this region? What's this region? What's this region? So we won't ask you all of them. We'll only ask you a few. But you don't know which ones they're going to be. So, know them all. Right. Okay. So you've got the specific regions. Then we also separate things into two big regions. Okay, and this will be important when we talk about the skeleton. So the axial part, or the axis part, is going to be the head, the neck, and the torso region. Okay, so this is axial. And then the appendicular part are your appendages, so your legs and your arms. Okay? So axial and appendicular. All right, so you've seen this diagram before. Now, with the people around you, see if you can answer this. So this is joining in our directional terms that we talked about last time and our regional terms that we just saw on the screen. See if you can answer this one. Okay, what do y'all think the answer is? 6 is correct. Okay, so what's more distal? The patella, which is your knee. Okay, so we are looking farther away down your leg. Okay, where's your femoral region? Your thigh region. Okay, your femur is what bone runs through there. So femur, femoral region. He is going to be more proximal than the patella. So that isn't your answer. What are your digits? Your toes, are they distal? Yeah. What's your tarsal region? Your ankle. So is it distal? Yeah. And then the ankle? Also distal. And so that leaves 6 as the answer. All right. So you see how we could ask a question that's got multiple things going together. You've got both your directional terms and your regional terms in the same question. All right, try this one. All right, guys. So the first one, what did he put out for the cubital region? For this region right here on the inside of your elbow. Good. Okay. Where did he give a shot if it's acromial? Shoulder. Good. And where did Harry have a bruise? His butt. Why did he have a bruise there? We don't know. Because he's not get a shot there. All right. So that leads us to our next material. Okay, so we've got directional terms, we've got regions. Now, this next part is going to be important when you start cutting things open in lab. Okay, so we are going to look at body planes and sections. So if I tell you to give a frontal cut, you need to know what is a frontal cut. Okay, so there's 3 different cuts. First, a frontal cut will give you a front and a back, an anterior and posterior. Okay, so right through there. Okay. So frontal, front and back. Next, transverse. The way I remember this one starts with a T. You always cross your T's and dot your I's, right? So if you're crossing your T, you're going to cut on that T cross. Okay, so it's going to give you a superior and an inferior part, a top and a bottom. Another way, transverse, top and bottom. Okay. And then the third one is sagittal. Sagittal gives you 2 sides, a right and a left. Okay, right down. If you have a median sagittal or a mid sagittal, that's going to be right at the very, very, very center. Okay. All right, so frontal, front and back, transverse, top and bottom, sagittal, 2 sides. Got it? Cool. All right, then see if you can answer this question. Mr. Bill is going to get cut into pieces. See how many pieces you will end up with after you cut Bill. Start over at every number. So this is one question. And start over on that one.
So they're not 14 because you're not adding them together.
All right. Number one. First, we're going to cut Mr. Bill at a median sagittal. How many pieces will we have of Mr. Bill? 2. What type of pieces are we going to have? A right and a left. So now we have a total of 2 pieces. Okay? Then we give him a frontal cut. What's that going to give us? A front and a back. So here's his back side that we've got coming off of here. Okay, and remember this is in half right here. So how many pieces do we have? 4. So the first one we have 4. Okay, now the second one, we start with the same thing. We have a mid-sagittal, we have a frontal. So we're at 4. Then we do a transverse cut, give us a top and a bottom, at the cervical level. What's the cervical level? At your neck. Okay, so let me make a comment about the cervical level. So when we talk about cervical, we're talking about like cervical vertebrae, like your C1, C2, things like that are up in your neck. There's also the cervix, which is part of the female reproductive system. Okay, and that you get cervical cancer when you get cancer of your cervix. That is in a different region of the body. Okay, so cervical level, we're going to cut him at his neck, this way across, right? A top and a bottom. So now we've got 1, 2, 3, 4, 5, 6, 7, 8. gonna put his head back on. And this time we're cutting him at the patellar level. What's the patella? Your knee. So he's going to be cut there, 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 and there. How many pieces do I have? 8. Okay? Right? Right? Okay. So, those questions, for some of you guys, you can see that 3D image in your head, and you can manipulate them, and you can cut them up into pieces all in your head. Some of you have to draw them out. Make sure you know what those cuts are. Okay? That's the purpose of the question. Okay. Body cavities. I believe this also was in your lab, right? Okay, so we're going to go pretty quickly. Okay, so we can divide your body into different body cavities. First, there are 2 big divisions. There's the dorsal cavity right here, and the ventral cavity. Okay, so those are 2 big cavities, dorsal and ventral. In the dorsal cavity, we can separate it into the cranial cavity, which has the brain, and the vertebral cavity, which has the spinal cord. And that's it. That's all you can do in the dorsal cavity. Okay? When we go to the ventral cavity, we can divide it a little bit more. Okay? So in the ventral cavity, we have 2 big cavities. We have the thoracic cavity, which is all this up here, and we have the abdominopelvic cavity, which is all this down here. Okay? So now we've taken the ventral cavity and divided it into 2 smaller cavities. But we're not done yet. Now we can take those 2 cavities and divide them into even smaller cavities. Okay, so we'll start with the thoracic. Okay, so in the thoracic cavity, we have a cavity around the heart. That's the pericardial cavity. Above the heart is the superior mediastinum. The cavities where the lungs are the pleural cavities. You have 2 of those, one on either side. Okay, so that's the thoracic cavity. Then the abdominopelvic cavity, we can separate into the abdominal cavity and the pelvic cavity. Okay? I missed it, but it's okay. You get the point. Okay, so body cavities. Again, make sure you can label them on the diagram. Okay? Alrighty. Next, membranes. So all of these body cavities are covered with serous membranes. Okay, serous membranes are a 2-layer membrane system. Okay, so 2 layers right on top of each other. The 2 layers have their own names. So there is a parietal serosa and a visceral serosa. Okay. When we look at our picture, let's see if this one doesn't work. A little bit better. Okay. There's going to be a layer of this membrane that sits right on the surface of the organ, in this case the heart. That layer is called the visceral serosa. Okay, and the serosas get different names based on what they're around. The one around the heart is called the visceral pericardium. Okay? But we'll get to those when we talk about the specific organs. Right now, just know that the one on the surface is the visceral serosa. Okay? Then we have a little space, okay? A little space that contains serous fluid. And then the outside layer is the parietal serosa. In this case, the parietal pericardium. Okay? And that parietal serosa is going to line the cavity wall. So it's actually attached to the wall itself. Okay? Both of the membranes, both the visceral and parietal layers, secrete our serous fluid. Okay, so the 2 layers never touch. There's a little bit of fluid that sits between them. Why do you think we have this design? Why aren't the organs just kind of thrown in your body? Protection. Okay, how does this protect your heart? Yeah, so you have, this is the heart. He is separate, he is right here. Okay, so it walls him off from everything else, protects him from the other organs, and from what else is going on. Okay, why else are our membranes important? friction. So that fluid between the layers helps make sure that the heart, when it contracts and it beats and it moves, doesn't experience friction rubbing against the wall of the body. Okay? So it's kind of like the oil you put in. It keeps everything lubricated and running smoothly. Okay? All right, so your serous membranes there. The next slide is an analogy. It says that you can compare this to a balloon. You can take a balloon that's partially inflated, and I tried to do this and bring it with me, but it didn't work. My balloon, I guess, was not big enough. When I tried to stick my hand in it, it just kind of went. Okay, so you can think of it like this. Stick your hand into a hypothetical balloon that has enough room in it. Then the balloon will cover your hand very, very closely. That's the visceral serosa. Then there'll still be air left in the balloon. That's in the serous cavity where the fluid is. And then there will be a parietal serosa, the outside of the balloon is still left there on the outside. And it's just showing you there's two membranes and a little bit of space between them. Okay? That was fun. All right. Abdominal pelvic regions. So this slide right here is the anatomist system. We have this up here to show you that this is what we could have you learn, but we're not going to. Okay? So it's lovely, it's beautiful. I love those terms. The hypochondriac region, the epigastric region, they're great. Here's what you have to know. You have to know the quadrants. The right upper, the left upper, the right lower, and the left lower. Beautiful, right? Okay. Now, the thing to remember when you're looking at anatomical things like this is things are labeled right and left based off of your patient. So this Skeletor guy right here, you are looking at right and left for him. Okay. So this is my right hand. So this is my right upper quadrant. To you, looking at me, it looks like it's on the left side. Okay. But it's right for me as the patient. Okay? But other than that, that should be pretty straightforward, your quadrant. Okay, and that brings us to the end of chapter 1. Any questions? Okay, so what you should be able to do now is go back to your chapter 1 objectives. Now that we have covered all the if there are things that you couldn't answer before or things that you weren't sure you had the right answer, go back through your notes, look at them now. Okay? So, that is your task before the exam. Alrighty. So now, while y'all are getting your chapter 2 notes ready, just give us a little introduction here. Chapter 2 is all about biochemistry. At least that's the section we're going to cover. When we looked at the hierarchy of living things, remember we start with atoms. Atoms make up molecules. Molecules make up organelles. Organelles make up cells. Cells make up tissues. Tissues make up organs. Make up organ systems. Make up. Fantastic. Okay, so we are working our way up. We're going to start on that atomic level. Okay, so that's where we're starting today. I've got some questions for you that we're going to chat about. First, does anyone know what the difference is between organic and inorganic compounds? Anybody tell us? Yeah. Organic compounds contain carbon, and inorganic does not. Okay, so organic has carbon, inorganic does not. Okay, which one of these do you think, I'll have you guys raise your hands, we're going to vote. Which one do you think is more important for life, organic things or inorganic things? Let's think about it for a second. Everybody ready? Okay. If you think that organic is more important, raise your hand. Okay. If you think that inorganic is more important to living things, raise your hand. Okay. If you think that both are important for living things, raise your hand. Okay, great question. Okay, so both are important for living things. We have to have both inorganic compounds and organic compounds. Let me back up and say this too. So our organic compounds that we're talking about in class, things that contain carbohydrates, sugars. Lipids are fats. Proteins, nucleic acids, or DNA. Okay, so those are really important for keeping you alive, right? If you stop eating, you die. If you don't have DNA, you die. But hopefully after the first part of today, you'll see that inorganic things, things that are not carbs, lipids, proteins, and nucleic acids, are also important for keeping you alive. Okay? So, we're going to start with the most important inorganic compound for you, which is water. Okay? So water is the most abundant and most important inorganic compound for living things. You are between 60 and 80% water. So 60 to 80% water in cells, depending on what type of cell you are. But then you are made of cells. Okay? So you're a lot of water. You are a bag of water. Okay, and we talked a lot about the process of homeostasis, keeping things balanced and stable. So I want to show you how these inorganic compounds help us maintain homeostasis. Okay? So water specifically has a couple things going for it. First, it has a high heat capacity. It does not like to change temperature. Okay? When you try to boil a pot of water, it takes a long time. Okay? Because it doesn't like to change temperature. It takes a lot of energy to get it to change temperature. So if you are made up of a lot of water, what does that mean about your temperature? It takes a lot of energy to change it. So you're going to stay about the same temperature. Right? Okay. So that's number one, high heat capacity. Number two is high heat of vaporization. So this relates back to our high heat capacity. But water, as you know, can be found in three different phases: a solid, a liquid, and a gas. Right? So this heat of vaporization is the energy required to change from a liquid to a gas. Water has a high heat of vaporization. It takes a lot of energy being put into that water to change it from liquid to gas. This relates to us in homeostasis because it has to do with sweat. Okay? When you sweat, what form is the water in? A liquid, and then it gets on the surface of your body, and eventually it's going to evaporate. Okay? This process is called evaporative cooling. It's not important, it's not in your notes. But when water evaporates off the surface, it takes that heat energy with it and causes the surface to cool off. Okay? So if you've gone to like a public restroom and you had to use that hand dryer to dry your hands off, if you start at the beginning when your hands are really wet, even though there's warm air blowing on them, they feel kind of cold because that water is evaporating off as the hot air hits it. But then as your hands dry off, then you can feel that warm air again. So it's not that the air is changing temperature, it's that the water is evaporating off the surface in the beginning and cooling your hands. So, high heat of vaporization allows sweating to evaporate and cool the surface. Okay? Number three, water is a polar solvent. Okay, what does the word solvent mean? It dissolves things. Okay, solvents dissolve things. So, Dr. Jones wrote this up here before, but a solvent dissolves a solute. The solute is what you put in. Okay, so the solvent could be water. The solute would be salt you're mixing in, or sugar you're mixing in. Okay? But water is a good solvent. Lots of things dissolve in it. Okay? And he does that because he is polar. What does polar mean in this instance? Anybody know? I heard somebody that wasn't loud enough. The electrons are shared unequally. What does that mean about the charge? It's more positive on one side and more negative on the other. Okay? So electrons have a negative charge, right? And they want to spend more time around this oxygen. So because they congregate over here, the oxygen ends up being slightly slightly negative, sorry. So you get a partial negative charge. The electrons don't want to spend as much time around the hydrogens, so they end up with a partial positive charge. So water is polar. Okay, so let's think of some things that we want to dissolve in the water. If we put something that is positively charged in, what's going to happen? A positive is going to want to go near the negative, and he's going to become friends with the oxygen side of the water. Right? They're going to like each other. If I put something in that's negatively charged, what's he going to want to do? He's going to want to spend time with the hydrogens. They're going to be buddies, right? Because they're opposite charges. If I put something else that's polar in, so let's add another water molecule. What's going to happen to him? The hydrogens are going to be attracted to another oxygen. The oxygen is going to be attracted to another hydrogen. So what you're going to end up with are all these water molecules that are kind of bonded together. Okay. So positive things can dissolve, negative things can dissolve, polar things can dissolve, lots of things can dissolve in water. About the only thing that can't is things that are non-polar, things that don't have a charge. Okay? Which we'll get to later when we talk about fats. Fats are non-polar. So fat and water, oil and water don't mix. Okay? So we need water to be a good solid because it makes up the majority of your body. So chemical reactions can take place within that water because things can dissolve in it and can do their job. Okay, number 4. Water is a good reactant in chemical reactions. For example, if you're prepared for your quiz today, you can answer this one. What is a hydrolysis reaction? Yeah. Yeah, you're fine, you're fine. Go ahead. You just have 3 people, right, to say here, you have a hand up. Yeah. Exactly. So you have a long polymer, you stick in water, it breaks monomers off. You add water to break it apart. Okay. What about a dehydration reaction? Yeah.
You take water away and it works in monomer from
Yeah. You stick the monomers on through a covalent bond. Okay? So both of those reactions require water. In hydrolysis, you're adding water to break it apart. In dehydration, you're taking away water to put it together. Okay? Those 2 reactions are going to be super duper important as we talk about our organic molecules. But they require water. Okay? And number 5 is cushioning. Water cushions things. Okay. So, water as an inorganic compound is really important. Our next group of inorganic compounds that are really important are salts. Okay? A salt is an ionic compound. So anything that forms with an ionic bond is called a salt. Okay? Salts will dissociate when they're put in water. So an example of a salt is table salt. Table salt is just NaCl. But when you put salt in water, it dissociates into a sodium ion, Na+, and a chloride ion, Cl negative. So you end up with a positively charged thing and a negatively charged thing. Okay? If we have an atom that has a charge, a positive or negative charge, what is that now called? Okay, they are going to be electrolytes, but they're electrolytes because they are ions. Okay? So because it has a positive or negative charge, it is now called an ion, and all ions are electrolytes. Okay? Yeah.
So it's only ion.
So sodium himself, he's an ion because he has a positive charge. to have one or the other, either a positive charge or a negative. Okay? So, they're electrolytes, which means they can conduct electrical activity, which is going to be super important when we get to the nervous system and the muscular system, because nerves conduct electricity. They send little jolts of electricity from one place to another. That's how they transmit information. And these little jolts of electricity are sent by moving electrolytes from one place to another. Okay? So you're going to move sodium ions, you're going to move potassium ions, and change up the charges. It's going to be great fun. Hope you are excited. I'm excited. Okay, now, how do salts play a role in homeostasis? Okay, so some of the salts that are in the body include sodium chloride, your NaCl, what we just talked about, so salt, table salt. Calcium carbonate, CaH2CO3, and potassium chloride, KCl. Calcium phosphates are found in your bone and your teeth, so they're what gives it the hardness, the mineral component. And they're most abundant in the body, those calcium phosphates. Okay, so salts in homeostasis. A couple of things they do. We just talked about this one. Sodium and potassium ions are responsible for nerve impulses and for muscle contraction. Okay, second one, hemoglobin. Where's hemoglobin found? Red blood cells. Okay, hemoglobin is the part of the red blood cells that are actually carrying the oxygen. So oxygen binds to the hemoglobin and then gets transported somewhere else. Hemoglobin doesn't exist unless there's an iron in the middle. Okay, iron is an ion, a positively charged ion. So no iron, no hemoglobin, no hemoglobin, no oxygen, no oxygen, no what? You got it. Okay. Number 3, zinc and copper ions, okay, are necessary for enzyme activity. We'll talk about enzymes later in this chapter when we get to proteins, but enzymes are required for all of the chemical reactions in your body. So, enzymes keep you alive, but no zinc and no copper, no enzymes, which means no zinc and no copper, you die. Okay? So, even though these inorganic compounds aren't specifically proteins, carbohydrates, lipids, and nucleic acids, they are necessary for you to stay alive. Okay? All right. Questions yet? All good? Okay. Now, we are going to talk a little bit about acids and bases. Okay, as we do, I'm going to give us a little summary cheat sheet over here on the side that we're going to make together while going through this information. Okay? If you have taken a chemistry class recently, then you know that there are multiple definitions of acids and bases, like the Bronsted-Lowry method, et cetera, et cetera, et cetera. We aren't going there. Okay? We're keeping things simple. So, here's what you need to know. First, an acid is a substance that releases hydrogen ions. Okay, so on my little cheat sheet over here, I'm going to say acids equal. We release hydrogen ions, so if there's an acid present, there's going to be a whole lot of hydrogen ions. Okay, that's the first thing on our little cheat sheet. Okay. The next bullet says that acids are also called proton donors. So that hydrogen ion H plus is the same thing as a proton, because in order for him to become H plus, he lost an electron, and all he has left is one proton. Okay. Then again, more chemistry stuff, but just know that hydrogen ion and proton, same word. Okay, same thing. Not same word. Okay, an example in your body is hydrochloric acid, or HCl. Where do you find this in your body? In your stomach. So it helps break down your food that you eat. Okay, so HCl releases hydrogen ions, releases protons. So you get a release of H plus and the chloride ion. Okay, so it's increasing hydrogen ion concentration. Okay, this last bullet, the concentration of protons determines the acidity of a solution. That means the more hydrogen ions there, the more acidic. The less hydrogen ions there, the less acidic. Okay? Now, let's see if we can infer some things. If we know that an acid has a high hydrogen ion concentration, the opposite of an acid is, so water base is going to have low hydrogen ion concentration. Okay. So let's see how we did. Let's put on the next slide. Okay, bases. Bases are considered proton acceptors. So acids give off protons. Bases suck up the protons. So there's less protons around them, which means less protons in the solution. Okay, an example is sodium hydroxide. When he separates, you get sodium ion and a hydroxyl ion. Hydroxyl ion is OH. If he is a proton acceptor and he wants to suck up that hydrogen ion, he's OH, hydrogen ion is H. When you stick them together, what are you going to get? H2O. You're going to get water. Okay? So there's an example of a base accepting a hydrogen ion. Okay, another example of a base, or another definition of a base, it's one of those other acid-base definitions, is that he can release hydroxyl ions. He makes a lot of hydroxyl ions. Okay? Important bases in the body are bicarbonate ion. We will spend a lot of time with our bicarbonate ion when we get to the respiratory system and when we get to the circulatory system and when we get to the renal system. So bicarbonate is a buffer. It helps maintain pH in the body. So we are going to spend a lot of time talking about how he does his job. Okay, ammonia is also a base in the body, and we'll talk about him when we get to the renal system. He's a waste product of protein degradation. Okay, now, go back. All right, so pH. Now, we know if you have lots of hydrogen ions, you have an acid. If you have a little bit of hydrogen ions, we have a base. So now we can say we need to measure the amount of hydrogen ions that are there and say, do I have lots? Do I have a little? Do I have somewhere in the middle? And our way of measuring hydrogen ion concentration is with pH. So a pH is a measurement of hydrogen ion concentration. Okay? This bullet here is kind of what we have on the screen already. The more hydrogen ions present, the more acidic. Now, this next one we need to add. It says the more hydroxyl ions present, the more alkaline. Alkaline is a base. So, low hydrogen ion concentration, but he has high hydroxyl ion. Okay? And the opposite is true with an acid. Okay? He's going to have low hydroxyl ions present. Okay. Now, pH. This next section that we're going to talk about, we are going to talk about how we derive the pH from the formula. This is not something you will ever be expected to do. This is not something we're going to ask you about. However, it is here to kind of explain what the process is. Okay, so I'm going to talk about it. If you don't want to pay attention, that's perfectly fine. I will tell you when we're going to come back together. Okay? So, the pH is equal to the negative log of the hydrogen ion concentration. Okay? And a log value is looking for what the exponent is when we have a base 10. So, for example, in gastric juice, hydrochloric acid, the hydrogen ion concentration in moles per liter is equal to 10 to the negative second. So that's going to be 0.01, right? 10 to the negative 2. Then, if we plug that into our equation, negative log of 10 to the negative 2 is going to give us negative 2. Okay, because we're just looking for what that exponent is. Two negatives cancel out and will give us just 2. So, stomach acid has a pH around 2 because our hydrogen ion concentration is around 0.01. Now, that's an acid, has lots of hydrogen ions. A base has a little bit of hydrogen ions. So our concentration then is going to be smaller, right? So let's say our concentration is that. That's smaller than that, right? Because we added some zeros. Okay? What is this in scientific notation? 10 to the negative 8. 8 to the negative 8. Okay, if we plug it into our equation, that's negative log 10 to the negative 8, which is going to give us negative 8, which is a pH of 8. Okay. Now, what I want you to notice from this, not that you have to ever solve this equation, but is this. If you have a high hydrogen ion concentration, your pH ends up low. If you have a low hydrogen ion concentration, your pH ends up high. So pH and hydrogen ion concentration are opposites. Okay? So if you have not paid attention to any of that mathematical junk, here's what I want you to write down. We have high hydrogen ion concentration in an acid, but you have low pH. Then on a base, we have low hydrogen ion concentration, but high pH. Okay? So stick that in your brain. We're going to use that a lot this semester. High hydrogen ion concentration, low pH. Low hydrogen ion concentration, high pH. Okay? Last thing to add to our cheat sheet, an acid is anything that has a pH below 7, and a base is anything that has a pH above 7. Okay? Anything right at 7 is considered neutral. Okay? It doesn't give off a lot of hydrogen ions. It doesn't take away a lot of hydrogen ions. All right. Any questions? Okay. Then Wednesday, you have your quiz at the beginning of class. Let me know if you have any questions while you're studying for it, and I will see you then. Has the attendance sheet gotten all the way around? Is it up here? Perfect.